Yeah, I asked you yesterday, we had say these equations for the integral properties, and I asked you to derive these equations for the partial properties. Just to show that quickly, this is on the website. I believe it's number 5. Well, straightforward. So this is your expression for the integral enthalpy or excess entropy. This was equation 168, x1, x2 times the sum of ai x2 minus xi. This was the integral property expression in the Redlich-Kister form. And you want to find the partial property of component 2, so remember x1, x2 is x1 minus x1 squared. This is the equation that we use, h2 equals h plus x1 dh dx2, equation 92. Plug into there, do the differentiation, collect terms, and you end up with h2 as x1 squared times that, which is the expression at 174 or something like that. So let's do that. There is no constant of integration, of course, because you're starting with an integral property, you're differentiating, you're not integrating. Just to repeat what I said about the Gibbs duo, maybe, however, were you to start with if you were to start with the expression for, let's say you were to start with this expression for the partial excess property of A, okay, then the model says that's the excess property of B. But remember, if you started this with excess A, this is all you have. You don't have the integral property. If you start with the integral property, if you've measured the integral property and fitted that to this equation, then you can differentiate that in order to get that expression for A and B, and then there's no constant integration because you're differentiating. However, if you were to start with this expression for h excess A and fix up all the terms hi, this expression for h excess B would be true plus a constant times xb. Okay? And that constant is unknown. To get that constant, you need a value of h excess B at some composition. Now, if you go all the way over to pure B, then the constant of integration is 0, because you know that h excess B is 0 and x is 1, so on. But if you fitted up this expression to h excess A, this expression for h excess B is only term plus a constant times xb, and you got to have an x. So remember, this is assuming that these expressions apply over the whole composition range, such that h excess B is 0 when at pure B. All right, so I wanted to talk a little bit about optimization. I know that's what everybody's doing, and this is on page 89, section 8.1. We're talking about, I'll give an example of an optimization of a binary system. I know that you've all done optimizations, but let's just go through one here for some, just for fun. I might show a few things you got to think about. I'm not trying to teach you optimization in this course. That's your So in a simple example of the optimization of a binary system, we consider the cadmium-sodium binary system. The phase diagram is shown in figure 49. So there's your phase diagram, which you have experimental points from several authors. You see there's two compounds. There's no solid solubility, these are considered to be effectively stoichiometric compounds. There's no limiting solubility, no one in the end member, so we assume the end member solid phases are pure solids. This very flat liquid is here, gives you some indication that, in fact, well, strong indication that you have positive deviations in the liquid, a tendency to demixing. And in fact, this is calculated, but you see that just below the liquidus, you actually have a metastable miscibility gap. That if you were to cool the liquid very rapidly, such that you suppress the formation of the solid, you would have a two-liquid region here. Now, you could never, suppress the solid fast enough. Well, if you suppress the solid fast enough and quench this down to room temperature at a very, very rapid rate by, say, splatting it between a couple of copper hammers, you could end up with an amorphous liquid, amorphous metal at room temperature, metallic glasses they call them. They're amorphous metals with metallic structure. If you did it in this region, however, you would find that there was a spinodal separation. Okay, anyway, that's not the optimization. What else? So you have these experimental data points. Actually, you see that one experimenter here, the triangles, made a flat here. In other words, he thought there really was a miscibility gap extending above the liquidus. He thought that this was that this gap actually, that the critical point here was above the liquidus temperature. And really, given the fact that with all of these points and the scatter of the points, that is possible. I mean, it is possible to interpret this as this coming up above the liquidus temperature. Putting everything together and looking at other data, our conclusion when we did the optimization was that that wasn't the case. But I mean, you're awfully close here. And I think there are really a number of diagrams in the literature where you have this kind of a curved liquidus where actually the miscibility gap goes above. And vice versa, you'll see a lot of systems where there's a small miscibility gap when really there isn't, because it's a really hard thing to. Anyway, that's incidental to what we're talking about. So if we go back to the thing here, so for electromotive force measurements, galvanic cells, several authors have measured the activity coefficient of sodium in liquid alloys. You know that in a galvanic cell, you can only measure one, you can measure the activity of one component, but not the activity of the other component. Do you all know why that's the case? You've all taken courses in electrochemistry? No? Galvanic cells? Concentration cells? Anyway, the activity coefficient of sodium, you really should understand the experimental techniques, or else you can't really evaluate the data that you're trying to optimize if you don't understand the technique. So we should read up about alloy concentration cells and galvanic techniques of measuring. Can I do that in 10 seconds? Okay, so the data are shown in figure 50. So in figure 50, okay, there we have, as far as figure 50, there we have gamma sodium as a function of composition at 400 degrees Celsius. This activity coefficient of sodium, you see it's equal to 1 for pure sodium. Goes positive because there are the positive deviations. I mean, positive. It goes greater than 1 because there's positive deviations. It comes back to becoming somewhat negative at the other side. This is pretty strongly confirmed. Actually, it's this evidence in fitting this up that wasn't consistent with the miscibility gap. So, anyway, so that's your activity coefficient of sodium in liquid cadmium alloys. Remember now that the activity coefficient of sodium has been measured over the whole composition region. So, in principle, then the activity coefficient of cadmium is obtained. You can fit this up, and if you fit this up, you'll get the activity coefficient of cadmium. And you do have your endpoint. It goes all the way to pure cadmium, where gamma cadmium is known. So you have your endpoint for your Gibbs-Duhem integration. But again, remember that you're integrating back from this point, so your activity coefficient of cadmium is not going to be as accurate as the activity coefficient of sodium, because you're integrating from this point, the slope of this curve. And the closer you get to pure sodium, the less accurate will your activity coefficient of cadmium be. Okay, so just keep that in mind, again, when you're interpreting your final results. So you say you've got a beautiful fit to this. This is the optimized fit I eventually get. You've got a beautiful fit to the activity coefficient of sodium. So clearly my activity coefficient of cadmium is going to be of the same accuracy. No, the activity coefficient of cadmium is not going to be of the same accuracy as this, because any slight change in slope here could have a big effect on the activity coefficient of cadmium. As well, so this is the sort of thing you've got to be looking at when you're thinking of optimizing. Don't just sort of put things into your optimizer equation and go think about what is actually being done. Okay, from the temperature dependence. Okay, so from the temperature dependence of the activity coefficient, the partial enthalpy was obtained via equation 114, which is the Gibbs-Helmholtz equation. Okay, so what being done here now is you see that the gamma sodium has been measured at different temperatures, and from d log gamma sodium dt, d1 over t, dRt log dRt gxs over t, d1 over t gives you hxs. Okay, I mean g. Or do it this way, RT log gamma equals gxs, and that's equal to delta h minus t sxs. Okay, so what you measured is log gamma sodium. Okay, you fit that up and that's been fitted up to at different temperatures. So we fitted RT log, we fitted GXS2 as a function of temperature, and from the slope you can get the partial heat of the excess entropy. But that's even less, that's of course less accurate, because if you measure this from 400 to 450 degrees, maybe your gammas are your log gamma is quite accurate, but I mean a slight error, since there's only getting such a small temperature difference, the slight error can have a huge difference in the slope, okay? So here's your value at one temperature, here's your value at another temperature. This is only a small temperature range. The slope of this is the excess entropy. A very slight change in slope can have a very big difference. Okay, so how wide was the temperature range over which the data were measured? If they were measured, if they got the temperature dependence over a 20-degree temperature range, you can probably just completely discount these values if it's measured over a large temperature range. But no matter how large a temperature range has been measured, it's still a derived property. It's not a directly measured property. So anything that's been derived is not as accurate as something that's been measured. This also goes back then, when you then say you've taken this data from the paper, what I did in this is from a paper that we wrote, and we actually didn't present this right here. The way we should have done it is the excess property of sodium. Well, what I showed you here, okay, let me show you what we did. And the thing is, don't do the same thing, or don't present it this way. So this is the excess enthalpy of sodium as obtained from the temperature dependence of the G excess. Okay, actually it's not badly fitted. Okay, but that is really a derived property. This was not directly measured. What was directly measured was GXS2, and this is the slope. Okay, so these points were never measured. These are the differences. What you really should do, then, if you're plotting this, don't ever plot the HXS, or look at the HXS. Look at the log gamma at different temperatures and show how well each of those curves is fitted by your optimization. Because then you're looking at the actual data that were fitted. You're not. Okay. Also, you will sit. Yeah. Okay. So, I always plot. Don't plot derived data. Don't plot data that are taken from the slope, or that are derived, or that are taken from adding another. Just look at the actual data that have been measured. So, or even, for example, another example, the activity. If some activity has been measured as the partial pressure of the solution divided by the partial pressure of the pure material. And let's say that the author has not measured the partial pressure of the pure material. He's measured the partial property of the solution and the partial pressure of the pure material you've taken from some other compilation. Don't plot activity, plot what he actually measured. That shows how well you fitted his data. Don't plot something that's been. Anyway, there we go. So the heats of mixing in this case it probably was justified in that these measurements were so accurate that you can see that the scatter is so small. It probably is justified, but I really should be fitting the gamma at show a curve for gamma at different temperatures and show how well it's fitted. Okay, so the excess heat has been measured. Okay, so those are basic. So what else is known in that system? Sorry, the integral HXS has also been measured by direct calorimetry. I didn't show that. The integral HXS was. System contains 4 solid phases, all assumed to be stoichiometric. We seek expressions for the Gibbs energy of every solid phase. We go through this. The heat capacity has been measured as a function of temperature. This is the so for the pure solid elements, for solid cadmium, the enthalpy at 298 is 0 by convention. The entropy at 298 is known from third law measurements. The heat capacity of solid cadmium has been measured and is fitted up to that equation. And so we get an expression for the Gibbs energy of solid cadmium as a function of temperature. That's right from your fact database. You get a similar one from you of pure sodium. The Gibbs energies of the 2 compounds have not been measured and are obtained from the optimization procedure. By the way, it's a total aside, but it's fascinating. CD2Na, it's a stoichiometric compound, and it actually isn't CD2Na, it's something like CD501 Na249 or something like that. The unit cell contains something like 800 atoms, and this has been proven by X-ray diffraction. It's amazing. That. Imagine these atoms depositing on the surface of this thing just correctly, and so that after you get 800 atoms, then the thing starts to repeat itself. I mean, how does it know, you know? It was Linus Pauling who actually came up with this when it was a tour de force of people realized that it wasn't quite right, the X-ray pattern. It's almost CD2Na, it's almost a very simple unit cell, but not quite. And you've got to go to something like 800 atoms until you get an actual repeat unit. And I mean, you know, the energy differences are minuscule. How the hell does it know that it's supposed to do that? Anyway, we'll treat it as CD2Na. So the Gibbs energy of the liquid phase is expressed as a polynomial. And this is where I brought this stuff in, so we already talked about it. The partial properties are given by this. I'm assumption is being made that the excess enthalpy and entropy are independent of temperature, that the delta Cp of mixing is 0. That's known as Knopfler. No, what's the hell's the name of that? What do they call it? Neumann-Kopp equation. If anybody talks about the Neumann-Kopp, Neumann-Kopp rule says the delta Cp of mixing equals 0. In other words, Cp of the solution minus XA Cp of A minus XB of Cp of B equals 0. We usually make that assumption. And if that's the case, then of course the heat of mixing, delta H of mixing, the delta Cp is d delta H of mixing dt. So if delta Cp is 0, then the heat of mixing is independent of temperature. We usually make that assumption, but sometimes there are temperature dependent values, and then you have to put them in. Okay, we talked about optimizations, least squares. I'll talk about those in a few minutes. Okay, all the data points. So we simultaneously optimize everything. As you know, the whole principle of optimization is you don't fit you could fit up the gamma, and you could fit up the HXS measurements to certain equations, and then you could fit up the liquidus measurements to other equations, and so on. But they have to be all self-consistent. The same enthalpy and entropy expressions that reproduce the phase diagram have to be the same ones that reproduce the measurements of the activity coefficients, and so on. So all the data are simultaneously optimized. You put these into your optimization routine, and you tell it find the coefficients that simultaneously fit all the data together. I don't know, do you people use OptiSage, Parrot, what we call Sergey's optimizer, or do you do it by guesswork?
Who wants us to do it by guesswork?
Do it by guesswork. Yeah, we usually find that's the best way around. It's sometimes worthwhile to start with an optimizer program, which I'll talk about in a moment, which simultaneously uses least square or something to optimize everything. It's a pretty good starting point. But then afterwards, you really have to adjust things. We can talk a little bit about that. Okay, whatever. By one means or the other, we found the following expressions for the excess enthalpy. Okay. And this expression for the excess entropy. And during the same simultaneous optimization procedure, the optimized Gibbs energy of fusion of the two compounds were determined. This is one way I presented it. Okay, but there's different ways of looking at this. But okay, remember you've only got, what have we measured here now? This liquid is here for cadmium. Only over this range do we have the activity of cadmium measured from the liquids, and it's almost going to be Rayleigh law over such a narrow range. If we knew the heat of fusion of this compound, then this is the liquidus for this compound. If we knew the heat of fusion of this compound, then we could, along this line and this line, obtain the activity of that compound in the liquid phase. Okay, because the same equations apply to we have RT log activity of a liquid minus RT log activity of the solid equals minus the heat of fusion 1 minus T over T fusion. If you assume the heat of fusion is independent. Okay. If it's a stoichiometric material, then you do that. So we get RT log activity of I on the liquid as the heat of fusion, as you've done before. Applying this equation along this liquidus will give you the activity of cadmium. Exactly the same thing can be applied along compound. If you go through the derivation of this equation, you see that it doesn't have to be an n-member element, it can be a compound. So I can write RT log activity of, and what is that, cadmium-2 Ni, activity of cadmium-2 Na on the liquidus, along here, okay, is equal to the heat of fusion of cadmium-2 Na. The heat of fusion of cadmium-2 Na is the heat required to go from the solid at that temperature to the liquid at that composition, at the same composition. 1 minus T over the temperature of fusion of CD2Na, which is 264, whatever, I can't read it. We have temperature of fusion up here. Okay, so if the heat of fusion of CD2Na was known, and remember now the activity of CD2Na equals the activity of cadmium squared times the activity of sodium. Want to prove that to yourselves? There's something to think about. Activity is equal to the activity of cadmium squared. Look at the definition of chemical potential. This really means the chemical potential of cadmium-2Na equals the chemical is 2 times the chemical potential of cadmium plus the chemical potential of sodium. Okay. Chemical potential is equal to dG dNi. Okay. Okay, let's go backwards. The chemical potential of something is equal to dG dNi. So the chemical potential of sodium is dG as you add some sodium. Chemical potential of cadmium is dG as you add dN moles of cadmium. If I add now 2 dN moles of cadmium and I put 2 dN moles of sodium, okay, if I add dN sodium moles of sodium and 2 dN moles of cadmium, then I've got dG is equal to mu cadmium plus mu sodium, but it's the same thing. Adding dN moles of CD2Na is 2 times dN cadmium plus dN sodium. In other words, I could take a pot here and I could add a small amount of millionth of a mole of sodium and 2 1/millionths of a mole of cadmium, or I could add a millionth of a mole of CD2Na. Is the same thing. Okay, and that then says that that's true, and of course from the definition of activity, then that's true. So, anyway, if you then get the, again this goes to what I've been trying to state, that if, when you're doing the analysis, think back to what, thermodynamically, what data do I really have here? Because just kind of trying to fit the liquidus up and things, you're losing track of what's happening. Okay, I can't, this liquidus, if I knew the heat of fusion of cadmium, and I might know that, then I could use this equation, or the computer could use this equation, or FactSage would essentially be using that equation to get me the product, at least the activity of CD2Na, which is a product. It would be giving me information about the liquid phase. But since I do not know the heat of fusion of cadmium, then this liquidus is not giving me any information about the liquid phase properties. But if I know the liquid phase properties, if I know the activity of cadmium and sodium in the liquid from other measurements, which I do because I have the activity of sodium has been measured, and that can be integrated with the Gibbs-Doom equation to get me the activity of cadmium. So now I go backwards. I know the activity from the other data. I know the activity of cadmium and sodium in the liquid. So I know this. So from the liquidus here, I can then go back and get the heat and entropy of fusion of the compound. Okay, so the liquid thermodynamic data and the liquidus data are permitting me to use this equation backwards in order to get the heat of fusion of the compound. And similarly, these liquidus points here permit me to get the heat of fusion of that compound, which I will probably assume is a linear function of temperature, the heat of fusion being constant, unless I really have some CP data. If I have CP data, sometimes I might have CP data for this compound, then I could use that. Now, you generally don't have the heat of fusion. Now, in this case, we have no data on that compound at all. We might have the heat of fusion, which would be very useful in that equation. But you can sort of back into the heat of fusion if you know the heat of formation. If I know the heat of formation of this compound, somewhere back here, shouldn't be doing this. I showed, I think this is worthwhile looking at, the relationship between the heats of fusion and heats of formation and so on. Anybody remember where the devil that was? It was in this section. Should be somewhere. Yeah. Figure. Anyway. Remember, figure 21 up here showed you the figure 21 here shows you the this was for the compound CaSiO3 in that system, stoichiometric compound. That's the heat of fusion. That was the heat of formation from the solids, and it showed you. Okay, so it gives you the idea of the heat of fusion. So, what figure was that again? Okay, so sometimes you know the heat of formation of this compound, you might know its CP, you might know its entropy at 298. That'll be different information. So, anyway, from this phase diagram analysis, we have no date on that compound, so it's the phase diagram optimization. We're going to back out from the diagram optimization the data for that compound. And what we're really getting then from the liquidist is the heat of fusion of that compound, which can then be related back to the, if we have the heat of fusion, we can then relate that back to the heat of formation of the compound from the definition. So from the simultaneous optimization then, we got two things. We got the heat and entropy of the liquid. So the heat of mixing of the liquid was from fitting the heat data, both the integral and the partial heat data. Remembering that the partial heat data is not all that terribly accurate. The excess entropy comes by sort of mixing everything together, and you get up with the Gibbs energy of fusion of the two compounds, which I fitted to linear functions of T. You should always look at the Gibbs energies of fusion to see whether they're reasonable in terms of the entropy. Remember, the entropy of fusion of an alloy, you look at it per mole of metal. You don't look at CD11 and A2, you look at 1/13 of CD11 and A2, because that's one metallic atom. And you look at 1/3 CD2 and A, and you see if it looks half-assed reasonable, that this has to be somewhere around 10, 5, 20, something like that. Not 300, not 1. It's a reasonable entropy of fusion. The above equations can be combined to give the Gibbs energy. You can combine these together to get the Gibbs energy information of the two compounds from the solid elements over that temperature range. And then you're going to have to make some sort of an assumption for the heat capacity of the compound. And again, you can use the Neumann-Kopp rule. As a first approximation, you can assume if you have a compound CD2Na, we often make a solid compound now we're talking about. Solid compound at say 298 degrees. What sort of approximation? Say we don't know the heat capacity, well then we could say the heat capacity of CD2Na is approximately equal to 2 times Cp of cadmium solid plus the Cp of sodium solid. That's the Neumann-Kopp rule. That's your first approximation. Second approximation, if you have nothing about the entropy, well you might say, well, the entropy at 298 of CD2Na, if you have that, would be 2 times the entropy at 298 of cadmium plus the entropy at 298 of sodium. That would be another approximation. You certainly can't do that for the heat, of course, because you have a heat of formation. Okay, the heat of formation is the heat of formation for 2 cadmium plus sodium equals CD2Na. Here we're assuming that the delta S for that reaction is 0. Here we're assuming the delta Cp for that reaction is 0. That's often well, none of them are great assumptions, but that's okay. That's not as good. And then you got, of course, the heat of formation, which is, of course, not equal to 0. If you do an optimization and you end up getting a... Okay, so from this optimization, I could use the Neumann-Kopp rule for the heat capacity. I could use the Neumann-Kopp rule for S298. And since I have the heat of fusion, I can get the heat of formation, and assuming that's constant, I would end up with the heat of formation at 298. Or if I knew the heat of formation at 298, then I could back calculate these from. If you back calculate the entropy at 298, this is also something worthwhile looking at, because this won't be zero, but it shouldn't deviate too far from zero. If you're mixing two solids to form another solid phase, you don't expect a huge change in the entropy. I might go along with 7 or 8 joules per mole, joules per atom. So that would be 3 times here, because this is joule. So, but if you're going up to something like 30, 40, you see this oftentimes in the literature too. This is fitted up, the heat of melt formation was known, and the optimization gave you an entropy of formation of 298 per mole of metal of 70 joules or something. It's wrong. Things are not, the entropy change is just not that big. You don't mix two solids to get another solid and get 70 joules. Remember, 70 joules per mole, that's like a heat, that's like an entropy of vaporization. Okay, so you've got to think of and even 10 joules per mole Kelvin is a typical entropy of melting. Now, you don't expect to form, think of the different, entropy as the disorder. If you're mixing, two solids to get another solid, you don't expect the entropy change to be greater than the entropy of fusion unless you've got a really, really ordered solid. Now, you might have an ordered solid, in which case the entropy would be positive or negative. The solids generally tend to be ordered, so you'd expect the entropy, this delta S, to be negative. Okay, so if you get negative, okay, negative 10, positive 10, you'll see it, but I mean, you got to think about orders of magnitude as well. So we always, in the papers we write, if you're calculating, in this particular example, you'd probably have to assume that was 0, but in other cases, if you had the heat of formation from other measurements at 298, you could then from these diagrams, I could have backed out the entropy. And if I found that the entropy change here was deviated more than, say, 10 joules per gram atom from 0, then I would start to question what I was doing. So you always look at your results. And I will also, this is something that's also rarely done, I would look at the heat and entropy of fusion, the entropy of fusion as well, to see if that's a reasonable value. Should be, for a metal, should be of the order of maybe 10 joules per mole. You can deviate a lot from that, but you can't deviate a huge amount. So this is okay. So the above equations can be combined to give the Gibbs energy information of the two compounds from the solid elements, but only over the temperature range of that phase diagram. If you're integrating down to 298, you're going to have to make assumptions about CP or something. Okay, and remember too, here I'm assuming that delta CP of fusion is equal to 0, which is reasonable over that range, but this certainly can't be true all the way down to room temperature. Delta CP is not equal to 0 all the way down, so you can't really extrapolate this equation right down to room temperature. Okay, so that was just an example of the sort of thing you should be looking at. What is really known in this, what is known and what is derived. What is known as gamma of sodium across here. Gamma of cadmium is not known across here, but it can only be integrated to the Gibbs doom. The gamma of cadmium obtained from this liquid, this is basically useless because it's going to be virtually ideal. You're not getting any liquid information really from the phase diagram directly. You're having to fix up the log gamma and the enthalpy and then working backwards in this particular case. Other diagrams, it may be the other way around. The phase diagram may give you lots of information on the liquid as if you have lots of data on the solids. Here we have very little data, we have no data on the solids, so the phase diagram is giving you data on the solid. If you know data on the liquid, other diagrams work the other way around. Okay. There are some hints about optimizations. This was a long time ago, but in this phase diagrams for Ceramus book, you've seen this volume, I'm sure, if you're working on oxide diagrams, the phase diagrams for Ceramus. You have that book? Tell him how you go buy that. Or he probably has it online. He has
the CD.
The CD, yeah, whatever. You must have the CD because it's 15 volumes. It's got all the diagrams. You can't possibly be doing optimizations in non-metallic systems if you don't have phase diagrams for Ceramus. Volume 7, the II, there's an introduction, which James Sangster and I wrote about 20 years ago, sort of called Hints on Optimization. And this was back in some of the primitive days when we were optimizing pretty simple systems. Okay, but it's a few pages that might be worth reading. It's way out of date, but that doesn't mean there are no principles in it. I'm not talking about all the equations we're using. These have been superseded by a lot of more sophisticated things. But just some of the ideas about if you have to make an assumption, if you're going to make an assumption about the liquid, would you assume the heat of mixing was 0 first, or would you assume the excess entropy of mixing was 0 if you had to do one or the other, and why, and this kind of stuff. And sort of the stuff I'm talking about here. Oops. So anyway, volume 7, introduction. Okay, you say, again, though it says you use the trial and error method of optimization, but let's look a little bit at the, this is handout number 11 on the website. You people, you haven't downloaded, you don't have to got your computers here anyway. You should, maybe bring your computers and have this downloaded, and then you can just look at these. Anyway, linear least squares optimization theory. This is not exactly what's used in OptiSage, but this is what's used in the Thermocalc's Parrot program. This is what is used in Sergey's, we call Sergey Dekterov's optimizer program, which people here use too for binary systems. It's much simpler to use than OptiSage. It's not as powerful, but it's an awful lot simpler to use. What I generally tell students here is use Sergey's optimizer program to get your first cut to your binaries, and then or maybe OptiSage if you can work through the input and output to OptiSage to get a first cut to your binary optimization. After that, really the best thing to do is is the sort of trial and error thing. But how do these linear least squares optimization program work? You have a programs, the linear OptiSage, Sergey's program, Parrot from Thermocalc, and so on are called optimizer programs. Those, right, they tend to be used too much. But in an optimizer program, you put in your raw data, you put in your liquidus points, heats of mixing, and so on, and somehow it puts everything together simultaneously, which is the whole point of optimization, and comes out with one set of coefficients for your, okay, so in the example we did with sodium cadmium, I would put in the liquidus points, put in the heat of mixing, put in, or the log gamma, put in the HXS of sodium and whatever other data I might have, and it would somehow mush all this together and fit the whole thing up to a to the proper equations and say these are the best. Well, I would have to tell what equations I want, fit it up to this equation, use so many parameters, and then it would give me the best value of those parameters. To give you an idea of how this works, it's really, how can you put in one program, I'm not going to show you the whole thing, but a simplified thing is how could you go to into one program in which you could simultaneously put in, do something very simple. You have let's say we have a heat of mixing. So we have some experimental data for the integral heat of mixing from direct mixing experiments, but I also have some data for HXS of B, which are being obtained either from partial mixing currents or maybe from the temperature dependence of a electrochemical excess. So I have partial properties of it. Let's say I have some partial properties of A2. These are experimental points, so I have partial property experimental points, and I have some partial property experimental points. So I'm trying to simultaneously fit the integral and the partial property experimental data. And the reason I can fit them in one operation is because the equations for the excess property, integral property, and the equation for the partial property have the same coefficients. Okay, so I'm trying to find one set of coefficients, H0, H1, H2, H3, which fit all the data simultaneously. All right, so in a simple way, that's what's going on. So I have one set of parameters. So these one set of parameters, so actually the entire, so the GXS2 for the liquid, for the phase, you have the H parameters and you have the S parameters. So the HI and the SI parameters together are the GXS parameters. So you have one set of parameters for the liquid phase, which will give you all the integral properties and the partial properties. Okay, so you need some sort of a mathematical least squares routine which permits you to simultaneously fit different properties to different equations, but those different equations have the same set of coefficients. Okay, so I have some measurements of hxs which must be fitted to this equation. I have some measurements of hxsa which must be fitted to this equation, and some measurements of hxsb which must be fitted to this equation, but those three equations all are based on the same coefficients. And they're all linear in the coefficients. It's h0 times something plus h1 times something plus h2 times something. There's no h2 squared or h1, h2 or anything like that. They're all linear equations in terms of the coefficients. Then you can use a linear least squares program. And here's linear least squares very rapidly. Linear least squares in general, you have a dependent variable y, which is a function of independent variables x1, x2, x3. Okay, so you've got fixed independent variables x1, x2, x3, x4, and y is your dependent variable, the thing you measure, and then b1, b2, b3 are the coefficients. You're trying to fit up all your experimental points to this equation. Okay, so dependent variable, independent variables, bj are the coefficients to be calculated. So you have experimental data points. You have x1, I going from 1, 2, 3, 4, 5 to up to n, each experimental data point has a number. So your first experimental data point is xi1. The independent variables are x11, x12, x13, x1m, and so on, and then you measure y1. And then at your second experimental point, you measure y2 at x21, x22. Okay, and you find the coefficients by minimizing the sum of squares. So the sum of squares, this is your experimental value, and this is the value that would be given by your fitted equation. So your fitted equation says that y is given by this equation. This is your experimental value. Okay, so you have basically you get one variable. If you had one variable x1, then you have experimental points. You're trying to fit them up, and you're trying to minimize the distance between the fitted line and the experimental points. And the way you do it is you minimize the sum of the squares. Okay, it's called the least squares method, and the reason you do that is buried in the mathematics, mainly because the mathematics is a hell of a lot easier if you use the squared than if you use the absolute deviations. Okay, but there's also some good mathematical reasons for it, which I won't go into. So we minimize the sum of squares, and there's all sorts of programs to do that. It's just a solving a set of linear equations. Okay, so if you look up linear least squares theory in any mathematics book, it'll give you this equation, or we'll show it. These are linear, the sum of linear equations in terms of the b's, and they're easily solved. And all sorts of software packages then will give you the coefficients b1, b2, b3, which minimizes the sum of squares here. So you say, well, in this particular case, however, I don't have a whole lot of different independent variables, x1, x2, x3, x4. I only have one independent variable, x, and this is the equation I would like. I don't want to fit it to a linear equation. I want to fit it to y. I have one independent variable, xi and y. My experimental points are pairs of values of yi and xi. And I want to fit it to this equation, for example. Okay, but what I do then is I simply say, well, the same thing is here. My x1 variable is 1, my x2 variable is x, my x3 variable is x squared, my x4 variable is x cubed, my x5 variable is ln x. So I have n experimental points, and I make this correlation. I let xi1 is 1, this is constant, xi2 is xi, xi3 is xi squared, xi4. So I'm telling it I have different independent variables, but they're all different powers or products of the same independent variable, so that's how it works. Okay, so this still has to be a linear equation, however, in terms of the b's. It's b1 times something plus b2. You can't have b2 squared or b1 b2 or b1 to exponent b1. Okay, but you can then have anything you want here, and you just make this. Okay, so then you make this. You make this mapping here, and you put this into your least squared program, and you get the values of b that best fit that equation. Okay, so then you end up with your one y versus x, and there's your equation. Okay, and let's minimize the sum of squares between the equation we fitted. Now you can go one step further, and you can have, well, I use these in slightly different form than here, but this is the okay, so let's say, however, now we have a number, now we're trying to fit up, as I said here, we have the heat of mixing. Well, here I wrote it as GXS, so let's just call it GXS instead of H, let's call it G. Alright, doesn't matter, so I've got GXS I've got some values, some compositions, I have G measured, G excess. At other compositions, I have measured G excess B, and at other compositions, I've measured G excess A. Okay, so the G excess points are going to be fitted to this expression. The G excess A points are fitted to this expression. I wrote this out not as a Redlich-Kister, but I wrote it in the regular polynomial expansion, but it doesn't matter. This is the equivalent to, remember I talked? I said you can write your expansions out in Redlich-Kister, xb minus xa, or you can just write them in terms of xb. If you do it in terms of xb, you still get the similar thing. The point is the GXS, the GXSA, and the GXSB are fitted to different equations, but with the same coefficients. So I have N1 data points in which I've measured GXS at different compositions, and they fit this equation. I have N2 data points in which I measured GXSA, and they must be fitted to this equation. And I have N3 data points in which I measured GXSB, which must be fitted to this equation, but the equations all have the same coefficients. Okay, so I number my data points from 1 to n, but from the data points from 1 to n1, the dependent variable is GXS, and the independent variable is this. For my data points from numbers n1 plus 1 to n1 plus n2, my dependent variable is GXS of A, and my dependent variable is this. And for the data points numbered from n1 plus n2 plus 1 up to n1 plus n2 plus n3, my dependent variable is GXSB, and my independent variable is now equal to that. These can all then be fitted into the linearly squared program to find coefficients phi. Okay, clear what's happening? And that's what the linearly squares subroutines do. Right, so you have different, I mean, a little more sophisticated, of course, because you also have the temperature dependence, but then the temperature dependence is just HXS and SXS, they're separate equations. And you'll have a similar equation then for every single phase, and then, but it's all brought into a linearly squared. These are still linear equations, these are all linear equations in terms of the coefficients phi. You can't use the linearly squared if you don't use the linear equation. Okay, so you have certain data points, the dependent variable can be different and the independent variable can be different, but they're all fitted into the same linearly squares program, so that's fine. You're minimizing the sum of squares. So you can then put in all your data points into one optimization routine. You put in all n1 plus n2 plus n3 data points, identifying which ones are GXS, which ones are GXSA, which ones are GXSB, and you say go to it. It minimizes the sum of squares and gives you the phis that give you the best fit. You can apply weighting factors in these programs. You can say some points are more accurate than other points. In that case, you can give weighting factors. Probably the simplest way is you just count 1.5 times, or count this point 0.1 times or something like that. You just give a weighting factor to the point. So that's the basis of the linearly squared subroutines. Now, not all subroutines use linearly squares. If you go to OptiSage, if you go to Sergey's program, it uses linearly squares, and that's how the Parrot program, which is being used all around the world, the thermocalc program is being used. The Parrot program is totally limited to polynomial expansions, however. It doesn't work for quasi-chemical or ordering or anything like that. Okay, and it's based on the linearly squares concept. Another way, OptiSage, OptiSage is a powerful program. The trouble is the input to it is real complicated to do, but it's worthwhile looking at. Ask in whole about Sergey's optimization program. I think you should be using it. The other way we do it is we're using some sort of a minimization routine. Basically, you're fitting everything directly. You have a liquidus point. This is what OptiSage does too. You have a liquidus point, say for example, and OptiSage takes that liquidus point. It takes you tell it which coefficient. This is the equation that I want to fit the thing to, and it basically calculates using successive approximations. It guesses the well, it isn't successive. ordered successive approximation. Guesses the value of the coefficients, gives you a calculated liquidus, and actually minimizes the distance between your experimental point and your calculated point. And you can calculate anything there. You can calculate, here you've actually got to fit the actual equations for the partial and integral properties. If you're using this technique, you can have fact-stage calculated eutectic composition. You can have fact-stage calculated vapor pressure. You can have fact-stage calculate all sorts of things. Okay, and then you can minimize the total deviation between whatever you measured and whatever fact-stage calculated. On the other hand, the weighting of these things can be real hell, because you can end up it looks good, but you're ending up giving it a huge weight to certain points, and then the other points are just kind of forgotten. And this is also the optimization. Using optimizers can be all sorts of randomly suggesting things I talked about an hour ago. Say you have system 1, 2, here you have log gamma 1, and this is log gamma 2. Remember I said they're connected by the Gibbs-Duhem equation, so in this region here, small differences in log gamma 1 can have a huge difference in log gamma 2. So if you've measured log gamma 1, you'll find, and you're doing a least squares, no matter what you do, you're fitting in log gamma 2 to some sort of equation like ax1 squared plus bx1 cubed, and this is all going to go very close to 0 when you end up with pure component 1. Okay, now you're trying to minimize the sum of squares, so I mean deviations from here, no matter what you choose these parameters, you can't have much of a change. So these points end up being very important. If you've got a point here that's off, because somebody's made a measurement that's silly, you know this can be off by say 15 joules, but you're at 99%. 1, so I mean it can't go like that. And yet this is going to really try hard to minimize that distance. Whereas you should be ignoring that point. Whereas down here, where the points can be quite accurate, I mean a very small change in the parameters can move this up and down, and it's not giving proper weight to that point. Or over here, if you have points of this here, you'll find that the weighting here is not as important as this, but it should be the other way around. So that's, well, that and other things like that are the problem with these optimizer programs. It's again, it's a even more extreme example of just putting the things into the computer and saying go to it and not thinking about what's happening. That's why, when we hear, like the idea of, do it by trial and error and see what you're doing. But to get a first cut, you could use the optimizer, and it's going to give you a reasonably good. Then you can see if it's done something idiotic, or if it has done something idiotic, and you can see, well, look, I've got points over here, and it's got way down here because it's been really busting its ass to try to get that. Except, well, let's just eliminate those points and do it again. Okay, so you can get yourself. Okay, but you got to be really careful when you're using these optimizers because it's just very blind. And also, how many terms do you add? Well, this is the other thing. How many terms should I use in my thing? I mean, I have gxs is equal to x1, x2, and then I'm going to say a plus b x plus cx squared plus dx cubed, or Redlich-Kister. How many terms do I want to put in? Well, I mean, if I put in 7 or 8 terms, I'm going to get a lovely fit. But I mean, I may get a lovely fit that looks like that. Obviously, you know that that's ridiculous, you see. So, but it doesn't know that. Okay, so you put in too many terms, you get a beautiful fit. Also, if you want, I mean, I say you want to extrapolate. So you measured the zinc cadmium. You've measured log gamma zinc over this region, and it fits pretty close to, say, a 1 coefficient equation, over 50%. Well, that indicates the thing probably isn't too far from regular behavior, so you probably can extrapolate it and get not too bad an integration of your Gibbs-Duhem equation. But then you get a little bit silly and you say, well, let's add a couple more terms just to get the fit perfectly over here. Okay, and then you get a perfect fit over here, but then when you extrapolate it, the more terms you add, the worse your extrapolation is going to be. Okay, because these are really empirical terms. They don't really have much physical significance. Too many terms, not only do you get a wiggle, but you try to extrapolate it and the thing can go crazy. So the more terms you use, the smaller is the distance that you can extrapolate. And you try and put in 4 terms and you get a lovely fit here, and then extrapolate it and it can do something crazy. You really have to plot the thing out to see what's going on. And then they say, how good is the fit? Well, there's this statistical criterion that the sum of squares, the minimum variance. Okay, the minimum variance, this is for statisticians. If you have a sample population of 3,000 you got 3,000 data points. And also, if you know that those data points should follow a certain physical reason that they should follow a certain equation, you have a whole lot of data points, you know they must follow a certain equation, then you can apply your minimum variance law to decide how many coefficients you should use. But first of all, here you never have 1,000 data points, you might have like 8. Okay, and secondly, the equations we're using, these polynomials, are not really physical equations. They make the reasonable, it's a reasonable form, but the more terms you add, the more. One term is okay, that's what I said. One term, if one term really fits, then it probably has some physical significance. That's your regular solution term. 2 terms, subregular, okay, the epsilons and so on depend linearly with composition. But if you go to 7 or 8 terms, the rest of the terms are nothing but a mathematical fit, and it's not going to extrapolate properly, and you cannot possibly use a minimum variance. If you use your minimum variance, you'll always end up with more coefficients than you should be using. So you're not really doing it. The least squares optimization programs like Parrot and OptiSage you're not doing a mathematical minimum. You're not really doing a mathematical thing. What you're doing is it's assisted curve fitting. Okay, it's not a statistical analysis because there are not enough data points, and the equations we're using don't have the physical basis that they really should have. So it's not a statistical analysis, it's assisted curve fitting, but there's nothing wrong with assisted curve fitting as long as you realize that that's what you're doing. And a lot of things we find in the literature, they don't realize that that's what they're doing. So, but I still think you shouldn't be doing it. I don't think you should be doing your optimizations completely from scratch because you're wasting some time. Start off with OptiSage or Sergey's program or something, and at least in the binaries. In the ternaries, I'm really against when you get into ternary systems, you can also use these programs in ternary systems, but there you really have so many variables and things, and you can go nuts trying to use these programs in systems greater than binaries. But for binary systems, there's some point to doing it. But then just look at it as a first cut, and then afterwards you got to think about the whole thing. And always think about it, as I've been trying to say 1,000 times today, in terms of if you didn't have the computer, what's really happening? If you have GXS of 1 here, then GXS of 2 is being integrated. And so what is really known and what isn't known, and what if I were doing this by hand, how would I have to do it? And that would give you some idea of the accuracy of what you're coming up with. And the final thing is, just because you look at an optimization and it looks beautiful, every single datum has been fitted, that doesn't mean, however, that all the other properties are going to be good or correct or even good. They might be or they might not be. You've got to think about it. The most flagrant thing is usually you have a very nice fit. The flagrant thing is you have a very nice fit to the liquidus over here of component 1, and then you assume that this means that gamma 2 in this region is good, and it can be really, really bad. Unless other additional measurements are available. Okay, that's it for today. So for next week. Okay. Series 12, 1 to 5. 5 to 7. That's the Gibbs-Doom equation thing. That's the stuff I talked about today. That's not on the quiz, but that's for next week. For next Tuesday, I'll talk about that. And the reading assignment, what I'm going to talk about next week now is I'm going to go to the Kohler-Tup-Bugiano, the going from binaries to ternaries techniques. That's on here, number 13, called Geometric Kohler-Tup-Bugiano paper. Read at least the first few pages of this paper, because this is what I'm going to be talking about material next week. This is on the the whole business of how we go from the binaries to the ternaries to the multi-component systems. And this is important, so that's the reading assignment. Okay, now I said that I could give you some review problems. I'll talk about these review problems on Tuesday. You might want to look at series 13. Okay, review problems for the series 1, 2, 3, 4, 5, 6, 7, 8. I mean, you can look through the devoir and see if there's anything that you think you don't know about, and if you don't, try it. Okay, and if you have any questions, then on Tuesday we can look at it. In terms of other things, though, I might suggest this is work that's already been done, material that would be conceivable, 27, 23, and 26. I will go over those on a Tuesday. And if you look on the website, you have the exam 2005, control 1, 1, 2, 1, 2, 3, and 4. And that should be on here. I do believe the numbers correspond to what's on the website. Old exams. And you scroll down to (2005) Control 1. Questions 1 to 4, which are in English this time. This was an exam that I gave in 2005 at about this time. This was considered to be a hard exam. Okay, just in case you panic this week. Everybody said, oh God, I don't know. Anyway, so, and I will put the, on Monday I'll put the answers to these on. So these are reviews for the exams, plus anything else you want to ask on Tuesday. I'll devote Tuesday to a review as far as necessary. If we finish the review and everybody's happy, then I'll continue with some new material. Okay, but so I'll start with the review, and then if you have any other questions from any other problem sets or so on that you want to talk about, we'll go over them on Tuesday. Next question, Wednesday is the test. What time do you want to do this?
Morning, 10.
What time, 10? 10 to... If it's 10, then you should plan to stay until 1. I mean, you might get done earlier, but I'll give yourself enough time. I'm not going to put strict limits on it, so don't. If you have to be out of here at 12, then let's start earlier, but if you 10 to 1 is okay? Okay, Wednesday, 10 o'clock. Stop.